I'm delighted today to invite Professor Mark Brosnan and his colleague Dr. Tom Arthur to speak to us about their autism research. Mark originally was an undergraduate in Manchester, worked in Greenwich and came here 20 years ago where he was invited to a personal chair, I think in 2016, and has been very active in aspects of autism research throughout that time. Tom has just completed his PhD. He did his undergraduate work in Exeter and came here for a master's and has done his PhD jointly between here and Exeter and has managed to achieve his PhD without any corrections. So for those of you who have a doctorate degree, to do that is quite an achievement. So he was born in Bradford-on-Avon, so he's definitely a local boy come good, and we're very pleased to have both of them come and talk to us about their specialist area. Very interested to hear what they have to say. So I think, Mark, you're starting off, is that right?
Thank you, Mark. Thank you for the invitation. It's a great honour to come and talk at such a prestigious institute, and thank you all for coming. So I'm Mark, and this is Tom here, who'll be talking later. So I'll be going through the first half, just giving a bit of background, really, about autism generally and autistic traits that are argued to be spread across the whole population, leading into talking about predictability, and then Tom's going to pick up that mantle and then carry on talking about predictability and how it may well be relevant for autistic people. So we're both from the Centre for Applied Autism Research, which is housed at the University of Bath at the top of the hill. And as Mark said, Tom is jointly, he's straddling the University of Exeter and the University of Bath to do his PhD. So we have lots of collaborations to be telling you about today. So there are, if you'd like any more information about the centre, the hashtag is actually Bath_CAAR, which you can't quite see there, or our email address and web page if you'd like any more information to follow up after the talk. Okay, so just to start off with on a terms about the language we're going to be using. There's a big debate within the autistic community about what the preferred language for talking about autism is, and whether it's an identity-first language, such as autistic person, or person-first language, such as person with autism. And many surveys of autistic adults suggest that autistic adult is the preferred terminology, that kind of identity-first language. So, of course, there are differences and different people have different preferences, but there seems to be more of a preference for talking about autistic adults than adults with autism. So we'll be using that language. But by and large, the general advice is, whatever you're talking about really, is to follow the lead of the person that you're talking to. So there are variations within that, such as person on the autism spectrum, person on the spectrum, child on the spectrum, and different phrases, all of which mean an autistic person. So we'll be trying to use that language today. So just to start off with, as you're here, you're probably familiar with the concept of autism, but just to characterise the clinical diagnostic definition. So there are two large overarching international bodies, the DSM-5 and the ICD-11, which really do coalesce around two key characteristics of a diagnostic characterisation of autism. The first is persistent deficits in social communication, social interaction, and this will be present across multiple contexts. And the second is restricted and repetitive patterns of behaviour, interests or activities. And both of these agencies agree that these are the key diagnostic features and both have to be present for a diagnosis of autism. So if you were to have persistent deficits in social communication interaction without repetitive behaviours, then you wouldn't be receiving a diagnosis of autism. You would, there might be some kind of social pragmatic communication issues rather than autism. So there's two aspects here that need to be met to get a diagnosis of autism. As you may be aware, the incidence of diagnosed autism has been increasing rapidly. In the States, they have an organisation called the CDC, the Centre for Disease Control, where they monitor the prevalence rates of all sorts of different conditions all across America, lots of different states, in children 8 years old. And they're always monitoring 8-year-olds so they can kind of try and monitor how prevalence rates change. So you can see the graph here. You know, when I was a kid in the 1970s, the rates were around 1 in 10,000. So the chances of meeting an autistic person who had a diagnosis were fairly minimal, up to the present day, where we're almost up to 1 in 36, almost 3% of the population in the States are getting a diagnosis of autism. So this is an American-based study, but similarly in a UK-based study conducted by one of Tom's colleagues at Exeter, Ginny Russell, you can see over the last 20 years, and this is looking at doctors-based records. So, very good data here. You can see there's a 787% increase in the diagnostic rates of autism in the UK over the past 20 years. So you can see a huge increase in the prevalence. And people have been asking clearly, what is the cause of this increase in prevalence? And all the data suggests it's greater awareness. It's greater awareness of autism. So people are now realising and being enabled to make the appropriate diagnosis. But the current levels have always been the levels of autism, but now the levels of diagnosis are catching up with what the actual levels of autism within society are. So, looking at are there any particular characteristics of the autistic population, and it seems to be occurring across all racial, ethnic and socio-economic groups. So there don't seem to be any biases in those kind of variables when you're looking across the autistic population. The big difference in terms of diagnostic criteria is that around 4 times as many males as females will receive a diagnosis of autism. We can be talking about that later, because there's a suggestion that maybe girls are being underdiagnosed through a process of a greater camouflaging that might be occurring, kind of masking difficulties, and possibly also girls in primary school settings being more supportive of their peers is therefore kind of giving protection to young female autistic girls in that primary school setting. So there's a suggestion that maybe there's a lot of underdiagnosed females within these statistics, in which case this increase may carry on until that masking issue is fully addressed within our diagnostic criteria. So, as I say, the CDC assesses rates at 8 years old, but actually, possibly as a result of this masking, girls are getting diagnosed later. And in the UK, the average age is around 15 or 12 years old, whether you're female or male. So, much higher diagnostic rates, and they would have been missed if you were just looking at 8-year-old type. Looking at 8-year-olds, then you've missed the people who are getting diagnosed above 8-year-olds. So they're just population estimates, but as I say, they're all heading in the upward direction. So Seinfeld said something that caused a lot of controversy fairly recently, where he said, I think on a very, I won't do an impression for you, because my American accent is dreadful, but he said, I think on a very drawn out scale, I think I'm on the spectrum. Basic social engagement is a real struggle. I'm very literal. When people talk to me and they use expressions, sometimes I don't know what they're saying. And it caused a bit of a furore amongst some members of the autistic community who thought that although he didn't have a diagnosis, he was trying to claim, I'm a bit autistic. And there can be a lot of antagonism against that sense of people who suggest they might be a bit autistic. Because clearly the diagnostic criteria, as that I outlined earlier, either you meet diagnostic criteria and you have a diagnosis of autism, or you don't. You don't have a diagnosis of, well, you're not autistic, you're a bit autistic. It's one or the other. It's a dichotomous distinction that clinicians are making. Either you have a diagnosis or you don't. But Seinfeld was saying he could kind of relate to aspects of that autistic kind of social activity, but clearly he's not referring to the restricted and repetitive behaviour side of things here. So these kind of common conceptions that people might say is, we're all on the spectrum somewhere, aren't we? And then go to the Mail Online to find an example of this, but you could go to any paper really. There are always news articles coming out saying every one of us is on the autistic spectrum. We're all a bit autistic. And again, this seems to be a misunderstanding of this distinct qualitative difference between having a diagnosis and not having a diagnosis. And we're just all autistic, but to varying degrees. And autistic people are very autistic, and some of us are minorly autistic, or some of us are a bit autistic. So again, that sense of being a bit autistic, which is again challenging to this distinction, again, this dichotomy between the diagnostic criteria that you either are autistic or you aren't. So this mail on online, but I could have chosen any newspaper, was reflecting on a huge study that was done. I don't know why it was done through Embarrassing Bodies, of all things, but it's done on Embarrassing Bodies. And if you went on Embarrassing Bodies' website and you looked on their web page, and you could see just between my mole checker and check your vulva was a mind checker. So you could go online and take a self-assessment. And the reason that, and they've got a lot of publications. Oh, what have I done? That was me, sorry. It's not a pointer at all. Was that it had well over 1 million people. So it was a very big population-wide study that was undertaken. And there were questions like this. I prefer to do things with others rather than on my own. And then it was whether you definitely agreed, slightly disagreed, or definitely disagreed. So there were 50 of these questions that came out that were teasing out how you self-reported your sense of social interaction with other people, different aspects of social interaction, things around friendship and maintenance of friendships and developments of friendships, but that kind of social communication and interaction, as well as more non-social aspects that may well be related to more restricted and repetitive behaviours. So 50 questions along those lines. And if you, it didn't matter whether you definitely or slightly agreed with it, you kind of got 1 point. And if you disagreed, whether that be slightly disagreed or definitely disagreed, then you got 0 points. So you ended up getting a scale score of between 0 and 50. Now this score between 0 and 50 is termed autistic traits. Now autistic traits are argued to be spread across the entire population. So we all have levels of autistic traits. So what this work has come from Cambridge and the work of Simon Baron-Cohen originally was looking to see this distinction between autism and autistic traits. So autism is the clinical diagnosis, and autistic traits is a dimension or a continuum that we're all on. And we would have a level of autistic traits from between 0 and 50. So what this graph is showing, and again, testing thousands and thousands of people, is that this dark line here is autistic people, and the dotted line is non-autistic people. And if you take these groups and explore these two groups, the autistic population as a group have higher levels of autistic traits than the non-autistic population. But you can see there's a big overlap here. You can have non-autistic people with higher levels of autistic traits, and you can have autistic people with lower levels of autistic traits. So overarchingly, as a group, autistic people have higher levels of autistic traits than non-autistic people, but at an individual level, you couldn't necessarily say whether a non-autistic person was higher or lower. It's just on average autistic people. So it's distinguishing two concepts of a diagnosis of autism from almost like a personality dimension of autistic traits. And some authors have referred to autistic traits as the 6th personality dimension. We have the big 5 personality, openness and extroversion and neuroticism, and saying maybe autistic traits is a 6th version of that and is spread across the entire population. So if you were wondering where you were, there's a shorter version as well, which is called the AQ10, and all this is online. And these are the kind of things that are assessing social skills, social imagination, social communication, as well as the capacity to switch attention, perhaps between different people who are speaking, and having good attention to detail is another feature of the AQ10. So there are 10 questions there, and again you would answer the extent to which you agreed or disagreed with them and calculate an answer. So as I say, all this is freely available. And if you're having consideration, I wonder if I might be autistic. This is not diagnostic in any sense. However, it's used within the NHS as a screen. So if you were to score very high on this, then that might be reason if you think, okay, I might be interested in taking the diagnostic process further. But this in and of itself is not diagnostic. So as I say, all this is freely available online from the Autism Research Centre at Cambridge, just as an initial screen for people who are interested in their levels of autistic traits. But having high levels of autistic traits doesn't necessarily mean that you're autistic. So the distinction is there's an autism spectrum. So if you were to have a diagnosis of being on the autism spectrum, you would either have a diagnosis or not. You'll be autistic or you're not. And then there's also an autism traits continuum upon which everybody is on. And overarchingly, autistic people tend to have higher levels of autistic traits than non-autistic people. Okay, now because of this sense of, you saw the increase in the proportions of people who are getting a diagnosis, which probably means there are a lot of older people who missed the opportunity to get a diagnosis in younger life. So there's probably a lot of undiagnosed older adults. And they may well choose to self-diagnose as autistic and think, I haven't got a formal diagnosis, but I'm going to self-identify as autistic, and potentially go and seek to get a diagnosis. Now, unfortunately, as you saw, the rates were going up by 787% in 20 years. What hasn't increased is the NHS funding by 787% to support autistic people. So the queues to get and the waiting times to get to see a clinician as an adult to see whether or not you're autistic are getting longer and longer. Years on years you might be waiting. So there are people who are self-diagnosed. So we did a study to see, looking at autistic traits in self-diagnosed adults and adults who had been formally diagnosed, were there any difference in autistic traits between these two groups? And what this graph shows with the two dotted lines is actually they were very similar, the two autistic groups. Whether they were self-diagnosed or formally diagnosed, in terms of autistic traits, these two groups were very similar and very different from adults who didn't have a diagnosis. So many organisations, including employers and universities, if you're approaching adults, are not asking for a formal diagnosis because there's a realisation that the waiting times to get through the clinical processes through the NHS currently can be taking years. So this sense of not necessarily needing a formal piece of paper to give you a formal diagnosis, and this celebration of autistic identity rather than the labelling of a diagnosis of autism falls very much within the neurodiversity movement. Now, neurodiversity, you may have come across this term, is, as a definition here, is looking to embrace neurological differences across humans and celebrate that difference rather than attribute a subset of that difference as being disabled or as being in some way impaired. What neurodiversity movement is looking to do is shift attention away from the negative aspects of neurodivergences and towards the positive aspects of them. So it's moving away, a focus away from the neurodivergence itself and towards the social contexts that turn neurodivergence into a disability. So it's trying to look at the broader context of society and what might constitute a disability and to what extent the social environment creates the disability and that sense of being disabled, rather than it being a more medicalised model of the individual as being disabled. So there's an example here of what's termed the double empathy problem. And the diagnostic criteria I gave you at the very beginning are the standard diagnostic criteria for autism, and it's sometimes it's called like an impairment-based or deficits-based account of autism, because it's saying, here's all the things that autistic people can't do. They're not very good at social interaction and they've got repetitive behaviours. So it's embracing a medicalised sense of a diagnosis of somebody who potentially might need some sort of support or intervention to normalise them. Whereas what the double empathy problem is trying to argue very effectively is it's not necessarily the autistic person that needs to be fixed, but it's the interaction between autistic people and non-autistic people that need to be addressed. And that people who are not autistic can also struggle to interact with autistic people, just as autistic people might struggle to interact with non-autistic people. And in a sense, it makes it's kind of blindingly obvious in that social interaction, almost by necessity, requires two people to have that interaction. Recently, people are looking at research that shows actually if you have groups of autistic people together, they're socially interacting just fine, and non-social people, non-autistic people are interacting with each other just fine. And the difficulty comes when autistic people are interacting with non-autistic people, and it's that interaction between the two neurotypes that is difficult, but that's coming from both sides. It's not the fault or caused by the autistic half of that conversation. It's caused by both communication partners. And where the difficulty resides is between the two communication partners. That's where the communication breakdown is, not being based upon one of those communication partners. And that there may be different struggles, but both communication partners are having their difficulties here. So at the Centre of Autism Research, Applied Autism Research at Bath, we're looking at different aspects of autism, but particularly we're trying to take a strengths-based account and trying to work with the neurodiversity perspective, think, well, let's focus on what autistic people can do rather than what they can't do. So this strengths-based approach is looking to see at potential strengths that may exist within the autistic population. And there's a list some here, and it's not to say that every autistic person is going to have every one of these autistic strengths, but attention to detail, or good visual perception skills, or good creative and artistic talents, or good mathematical and technical abilities, or good interests or expertise in these areas, or good strengths within their character, such as honesty and loyalty, can all be present in different members of the autistic community. So it's reconceptualising and trying to think about what are the strengths within this population rather than focusing on that deficit model that comes from the diagnostic criteria. And with my colleague Chris Ashwin at Bath, we've been looking very much at strengths in thinking and reasoning. So you may have seen this problem before. There's a quick thinking and reasoning problem for you. A bat and ball together cost £1.10p. The bat costs £1 more than the ball. How much does the ball cost? And the answer is 10p, thank you. So we have an incorrect answer from our audience, and the vast majority of people say this. We ask our students who at Bath, they're AA students, and you ask them this question, and 70 or 80% of them will say 10p, because the question is written in such a way to lure you into this intuitive answer of saying, bat and ball £1.10p, bat £1, ball 10p. I could just do that, you know, without having to think too much. However, has anyone worked out what the actual answer is? 5p, thank you. So there's a correct answer of 5p. So if the bat, yes, well done. So if the ball was 5p and then the bat was £1 more than that, that would be £1 and 5p, plus the 5p is £1.10. So a small proportion of people do get the answer right. So what we've been doing is giving this out to students, and it's international. Students at Harvard, 70 or 80%, are all getting the wrong answer for this, and questions like it that are written in a way that lure you into a wrong answer. But if you think about it, you get to the right answer. So this is a kind of classic finding we would find, is that autistic people on average are kind of almost getting about 70% of these questions right, whereas non-autistic people are getting less than 40% of these questions right. So we've tested this over different sort of paradigms, and there seems to be a real strength here in autistic thinking and reasoning, demonstrably over and above that of non-autistic reasoners. So another example of these kind of problems you might ask. So you might have this kind of scenario, and if a ball was to start shooting down this tube, when it shot out the end, which way would it go? Would it follow around the dotted arrow, or would it follow around the straight arrow? Similarly, okay, you're in a flying aeroplane, a little hatch opens, and you drop out a ball. What trajectory would the ball take if you threw it out of this flying plane? You know, would it go like this? Would it go like this? Would it go like this? Now again, the kind of this is sometimes called intuitive physics, because you might not have actually learnt this at school, but you might have some kind of understanding of trying to predict the physical world. And if you have an understanding of kind of, sometimes it's called intuitive physics, kind of basic understanding of I can predict how these things are going to be happening in the physical world. And the answers, the correct answers, for those of you who work through are the solid lines there. And again, autistic people are much better, they're not trained physicists or engineers, better at identifying these kind of, predicting how things are going to happen in these kind of environments. Without any formal training, just seem to have a good sense of being able to predict these physical engineering type principles. So there seems to be, again, another real strength. So these kind of strengths that we're talking about are strengths that are associated with logical thinking or intuitive physics and thinking about the world in a logical, predictive kind of way. And Crespi has pulled all the different strengths together in autism, and he calls it, if you look at all the different strengths, there's something that unifies all these different strengths in autism, and he calls it predicting rule-based patterns. And what autistic people seem to be able to do is, if there's a pattern out there, if there's something that's following a pattern, they can work out what that pattern is. So if there's something to predict, they can predict it a lot better than people who aren't autistic. So Crespi argues that it doesn't matter which of the strengths you're looking at in autism, there's a unifying feature underneath them, and that's predicting rule-based patterns. So just to give some examples, to finish off on some examples that highlight this rule-based patterning, this study was it wasn't by us actually, it was by Goris in 2020. And what they were doing here is they simply presented people with either a random sequence of notes or a highly predictable sequence of notes, and the order was randomized and all that kind of thing. Just asked them, which do you prefer? And now this was related to autistic traits that I was talking about, that dimension, rather than looking at autistic people compared to non-autistic people. So what Goris found was that the higher the level of autistic traits, the higher the preference for the predictable sounds over the non-predictable sounds. So people who had low levels of autistic traits either preferred the random sounds or had no preference, whereas the preference for the structured, predictable sounds got greater and greater, that preference, the higher and higher your levels of autistic traits. And these were people in the general population. So that's within the auditory world. Also within the visual world, they had a study where they showed you one picture and then they showed you a second picture and then asked you how much did you like that second picture. So you have to bear with me with this one. So the first picture they showed you was an outline of a picture, and the second picture was the full colour version. Now, the difference was sometimes the outline predicted what the full picture was going to be. So it was the outline of the full picture, and sometimes it wasn't. So sometimes you got a warning of what the picture was going to be, and it was predictive. And then you were asked how much you liked that picture. And again, there was a very similar pattern. The higher your levels of autistic traits, the more you liked the predicted pattern compared to the patterns when they weren't predicted. So again, a preference for prediction increasing with your levels of autistic traits. Now, this was all done in adults with autistic traits. The final study I'm going to tell you about before handing over to Tom and talking more about his work on prediction was looking at children. And these were 7-year-old children, and they were either autistic or non-autistic children. And they had a quite an engaging little scenario where they had children in a room, and they had a little stage with a closed curtain. So in the initial condition, the stage would be there, and then a light would appear to light up the stage, and then the light would go off, and the curtain would open immediately, and a toy would be revealed. Now, in this situation, the children, whether they're autistic or not, went and played with the toy. And actually what the study was looking at to see was, is there any difference in different types of toys when the curtain is revealed? So they did this multiple times. But they found that actually there wasn't, it doesn't really matter what the toy was. Children went and played with the toy when the curtain went up. Now, the interesting thing here is they had a second condition, which was almost identical. Now, in the second condition, the light went on for 6 seconds again, but when the light went off, there was an unpredictable delay before the curtain opened to reveal the toy. So that was the only difference. Rather than there being a highly predictable curtain raising as soon as the light went off, there was a random delay before the curtain went up to reveal the toy. Now, in this condition, the autistic children played much less with the toys than the non-autistic children. Something about, and the only thing that was different was the unpredictability of when the curtain opened to reveal the toy. These were different conditions, but the toys were the same. So that unpredictability seemed to be in some way unsettling the autistic children, so they no longer engaged with that behaviour. And it's a behaviour that presumably they did want to engage in, because when there was no unpredictability, they were very happy to engage in it. So the authors concluded that these findings suggest there's an appropriate starting point for therapeutic intervention with autistic children might be to focus on shaping social play in highly structured and predictable environments. Now, the one reason I'm highlighting this is because they said this in 1980. So about 40 years later, people are starting to think, I wonder if predictability is important for autistic people then. And this links into what's sometimes called the golden equation. And Bearden has suggested, who's another autistic academic, is to say, is autism plus environment is the outcome. And what you really need to think about, if you're trying to support autistic people, is the environment. And the more predictable you can make an autistic person's environment, the better their outcomes are going to be. So again, it's shifting the focus away from the autistic person as somebody who needs to be intervened with to the environment that needs to be addressed to enable the autistic people to thrive and get the best positive outcomes. Okay, so finally, about 40 years later, we've caught up with the sense of the role of prediction. And this is where I'm now going to hand over to Tom.
Thank you, Mark. Okay, so as Mark's just talked about there, the role of predictions has been discussed for quite a long time within the autism research world. However, in the last decade or so, this discussion's really changed, and this is due to a number of quite high-profile theories that emerged after the year sort of 2012. So the first of these theories essentially argued that autistic people have difficulties in the ability to make and use predictions. Now, the reason this was such a sort of high-profile theory is these authors argued that these difficulties ultimately can contribute to lots of different autistic-like traits and behaviours. They can explain why autistic people might struggle in some social environments, for example, when the environments are inherently unpredictable. It can explain some of their behavioural differences that Mark's just been focusing on there. But it can also account for differences in how sensory information is perceived, for example, or why autistic people might show difficulties with learning certain skills or with certain attentional difficulties, for example. Now, this has led to a sort of explosion, if you like, of further high-profile theories within this topic. These models in particular take what we refer to as like a neurocomputational model of the brain. So they see the brain as almost a computer or a like prediction-generating machine. And they're able to isolate certain networks or certain functions in that computer, and they say that these are different in autistic people. And as I say, these all have slightly different hypotheses or theories, but the sort of broad message from all of these theories is that autistic people have differences in how they make or use predictions, and these differences cause a lot of autistic-like traits or a lot of behavioural differences across their day-to-day lives. And unsurprisingly, these pretty bold claims have received a lot of attention within the media, within the neurodivergent community, and also within academia. And this is something that we became really interested in sort of 3 or 4 years ago as I was starting my PhD, or slightly longer than that now. And that's specifically because we were looking at the topic of sensory motor difficulties in autism. Now, when I say the word sensory motor difficulties, what I'm referring to are movement-related difficulties. Research suggests that most autistic people experience difficulties relating to things like clumsiness or hand-eye coordination differences, differences processing sensory information, or differences learning certain movement-related skills. And as I say, these have been focused on a lot less in research and in the media, and if people do want to read up on them, the NAS and some of the web pages we'll show at the end have some really interesting work on some of this stuff. But as I said, the common theme that's emerging in research is that most autistic people experience these difficulties, and that these difficulties can impact on things like independence, on health, on quality of life. But as I say, there's a lack of research, and there's also a lack of evidence-based support or programs that can actually help autistic people manage these difficulties in their day-to-day lives. So the aim of my PhD was to try and address this sort of gap in the research, and we were particularly interested in some of these, in the role that prediction might play here. And that's because prediction is fundamentally important in how we move and interact with the world around us. So firstly, predictions are very important in how we perceive sensory information. If you take a sporting task like tennis, the ability to see this tiny little green blob of light in what is a very complicated and sort of moving visual scene and environment, the ability to do this is theoretically underpinned by the brain sort of predicting where that green blob of light is and predicting what it means and so on. So predictions are really, really useful in guiding these sorts of perceptual abilities. And actually sometimes, whereas predictions in pretty much everything we do in our life are important and are useful, sometimes our predictions can cause some quite weird perceptual effects, right? Here we predicted the sky was in a certain place, and actually those predictions in that context might not have been accurate. But predictions aren't just important in how we perceive sensory information, they also determine what sensory information we look for and attend to. So if we go back to our tennis example, when Andy Murray's tracking a ball, research suggests that he's not trying to sort of constantly track it and keep up with it. It's moving at over 100 kilometers an hour, so he's probably not going to be very successful if he does this. What research suggests is that our brain makes predictions about where the ball is going to be in the future, and our eyes will skip ahead to where that location is, where we predict. So, because we've been talking for a little while now, I'm going to do, and also because I have a very short attention span, I was just going to do a bit of a, break this up a little bit with a video at this point. So hopefully everyone can still see this, and hopefully this works well for the audience on Zoom. So I'm actually going to mute it, and I'm going to play it now. So the aim of your task in just a minute, what's going to happen, don't worry, I won't put anyone on the spot, but the aim of the task here is for you guys to track this golden snack, this golden object, as it's moved around. Okay, so I'm not going to put people on the spot, but hopefully you have one that you think it might be. And so hopefully in a second, that's going to be revealed. Okay, so that was easy, right? So let's make it a little bit more complicated now. So same task, try and track where this golden snack is. Yeah, as a bit of a clue, the golden snack will be under a pink cup at the end. Less confident this time, but still people think they've got it. So once again, the answer's going to be revealed. No, definitely not. But keep watching this, because this is something that's also interesting. Did anyone see the duck? So, as we can see at the top of the screen at one point, seems like a couple of people might have seen the duck. Did anyone spot the fact that at some points there was 5 hands in the video? This was a little bit more subtle, actually. But you can see that at a few different points there's an extra person moving some of the objects. And the final one, this isn't to make you all feel really bad, by the way. But the final one, I don't know if anyone noticed that actually at the start there was blue cups in there, and by the end all of those blue cups were actually green. Okay. So if we now go back to slides. So hopefully that example, as I said, it was hopefully a little bit of fun, but also what that's showing is our ability for predictions to guide what we look at in the world around us, right? So when you guys were doing that task, you were making predictions about where you thought the useful information would be on the screen, and your eyes were sort of saying laser focused on this useful bit of information. Now, the task was for you to track that. I wasn't saying for you to look out for all these other things. So actually, as far as I could tell, lots of people seemed pretty happy with themselves that they were able to keep their attention focused on that point. However, you can also see that if you're predicting one thing and your attention is sort of tunnel vision focused on that thing, you're maybe missing things, or you're not attending to other things that are going on in the world around you. And so your predictions that you make are really important as to how you see the world around you and how you interact with it. And finally, from the perspective of movement, we know that predictions are really important in determining our sort of action behaviours. I don't know if anyone's sort of done that thing where you go to pick up a bag before you go on holiday and it's way, way heavier than you were predicting. My partner's very good at sneaking loads of things in last minute. So you go to pick it up and you sort of have to take a few attempts to lift it up because it's a lot heavier than you predicted and you haven't sort of used enough muscular outputs to pick it up. Another example that you get a lot in Bath, I find, is that you get a lot of doors that look like they're really, really old and really heavy, and actually they've been sort of renovated fairly recently, so you end up sort of throwing them back. It's a similar thing. But actually, what I'm giving there is some examples, again, where predictions are maybe inaccurate, and that's not actually particularly common. You actually think of what you do in your day-to-day life. You're constantly picking up things, you're constantly interacting with things, and you're not consciously making predictions about how much these things weigh or what they feel like. Your brain is just constantly doing it in a way that's relatively effective and accurate. So hopefully I've convinced you there that predictions are pretty important in sensory motor control, and what my research was really interested in is how these predictions might be different in autistic people. So we got participants to come into the lab and they completed basically an object interaction task. So they lifted up an object, they reached out, they grasped it, they picked it up, whilst we undertook a number of quite precise measurements relating to prediction. So firstly, we tracked participants' hand movements. So hopefully you can see in some of these videos these sort of grey dots here. These are being tracked by cameras and we were using what's called motion capture analysis here to do it. I don't know if anyone's seen some of the new films, like the new Lion King and the new Jungle Book. You'll see the actors, when they're filming this, all have these little dots on them. And then what you do is you sort of visualize, so you track all the movements and you then use it to visualize, so this person now looks like an animal or a mythical creature or whatever. We're essentially using the same technology here, but instead of visualizing things, we're measuring things at like over 100 times a second to look for really precise movement variables. We also had, so our participant, you can just about see there, was wearing these sort of glasses type things, which are measuring eye movements. So as I just showed that video there, we were looking basically at what people are looking at for how long, and some of these sort of precise measurements there relating to prediction. And finally, we were also interested in the sort of forces that are used to pick up and interact with these objects. So what did we find? Well, the first thing we did when participants came into the lab is we sort of put these three objects on the table, and before they lifted them, before they interacted with them in any way, we just asked them to sort of guess and give a number as to how heavy they thought these objects would be. And both autistic participants and non-autistic participants, everyone that came in the lab, unsurprisingly predicted that this larger object would be heavier than the smaller one. So that's pretty unsurprising, right? For this specific study, these three objects were actually exactly the same weight. So they require the exact same force to pick them up. They require the exact same movements. The only thing that's different is your predictions going into the task. So what do I sort of mean here? Well, the handle that they used to pick up the objects, we had these force transducers within them that could basically see how much participants were like squeezing them and how much force they were using to lift them. And what we have here is a graph that's basically showing how much force was used to grip these objects. Now what we have, if we just focus on the first trial here, so trial 1, this is the first time they picked up these objects, you can see that the larger object is being picked up with higher forces than the smaller one. And that makes sense, right? Participants are predicting that the larger object is heavier than the smaller one, so they're using higher forces, despite the fact that these objects are actually the same weight. Now these are non-autistic participants. This is something that we always see in these type of studies. And what you can also see is these blue lines are getting closer together then over time from trial 2 onwards. So as people learn that these objects are actually the same weight or a similar weight, they use similar forces to grip them. So what was really interesting in this study is that we found that autistic people did pretty much exactly the same thing. This suggests that actually, contrary to some of those big high-profile theories I talked about a second ago, the ability to make and use predictions is not necessarily different in autistic people. And this wasn't just shown when we looked at sort of force behaviours. This was shown when we looked at eye movements. So what we can hopefully see in this video at the top, press that button, Mark pressed earlier. Hopefully you can see that little red cross. That's where people are looking in this task. basically you can see a little bit like the tennis I talked about earlier, that the eye is going just a little bit ahead of the hand based on where you predict the object's going to be in the future. Autistic people showed very, very similar eye movements in this way. And hand movements were generally, even though we're using these really precise measurement tools, hand movements were generally very, very similar as well. So again, this ability to make and potentially use predictions does not appear to be different in autistic people or in individuals with high autistic-like traits. However, we did see on some very specific trials and some very specific conditions, there were some really, really, really clear sort of differences emerging between autistic people and non-autistic people. So whilst autistic people are able to use predictions, they seem to be using them differently in some contexts. And so this kind of links back to the stuff that Mark was talking about earlier. Clearly, we have to look at the role of the environment here. We have to look at the role of environmental predictability or uncertainty if we're going to look at these effects. So we've tried to do this using the technology of virtual reality, or VR. Now, for those of you that are maybe unfamiliar with VR, VR's, you can see it here. It's almost like some goggles that you put over your face. And whilst you have it on, you can basically interact with and see all these sort of virtual computerized things in the world. So we have a nice little video here. This person is actually just in their lounge. They're just in their lounge at home. They're wearing one of these headsets, and they feel like they're stepping out on a tiny little wooden plank at the top of a skyscraper. Now, I don't know if anyone's done this before. I don't think lucky's the right word. I've done this a few times, and honestly, your hands get really sweaty. You're really sort of trembling as you do it. It's really, really difficult. Now, this is an example of where sensory information, again, is affecting our movement thanks to predictions. We're predicting lots of things whilst we're doing this task, and this makes the very basic skill of just walking along your floor very, very different. Now, you'll be thankful to know this isn't a participant, okay? This is just a viral video. Our study, we didn't use this task. We used a much more controlled task. We specifically focused on the skill of racquetball because this is the type of skill that autistic people can sometimes find difficult to perform and learn. Whilst they performed this task, we tracked their hand movements and their eye movements. So they were hitting balls back towards the target, like you can see here. And these little green dots that you can see sort of spread around are basically where someone's looking in the task. Now, participants wouldn't normally be able to see these things, but I've just shown these for the purpose of this video. And hopefully what you can see in this video here is that this ball looks like and is behaving just like a tennis ball does in the real world. However, that wasn't always the case in this study. So on some trials, we sort of provided balls that bounce in a really, really unpredictable way. I love this example. It's quite an amusing example. You can see here the participants sort of turning around as if to be like, what's gone on here? Like, what's just happened? And that's because this ball's bouncing with an even higher level of bounciness than those like little rubber toy balls you get as a child. So this is like nothing you'd ever see in the real world. It's a really unpredictable stimulus. And so what we did in this study is we sort of created periods of time where the ball was bouncing in a really predictable, stable way, and periods of time where ball bounciness was unpredictably changing in a way that was really hard to sort of keep track of over time. And what did we find? So what we have in these graphs here is just basically the percentage of balls that were successfully hit by participants in the task. And we can see that generally the sort of grey bars for autistic participants are a little bit lower than those lighter bars. So this is just basically showing that generally autistic people did find the task a little bit more challenging, which, as I say, is consistent with a lot of research. What you can see here is that in the unpredictable, in the volatile conditions where bounciness is changing in a really unpredictable way, you can see that these differences and these difficulties were much more pronounced. So this feeds back to the idea that Mark was talking about earlier, that autistic people might be struggling with more unpredictable and unstable task environments. What about the specific predictions that people were making? So what we have on these graphs here is basically how high up people were looking at a given moment in time. And I'll try and talk you through this slowly because I appreciate that this is just a bit of random numbers at this point. But this is to begin with early on in the task. And what you can see is that where people are looking is sort of closely following the trajectory of the ball. You can see in this example at the top here that it basically participants will closely track the ball to see the sort of speed that it's going, the direction it's going, and they'll get sort of early information. But then what we see is what I talked about earlier. We see this sort of predictive eye movement. So people tend to, their eyes will sort of skip ahead of the ball based on where they predict it's going to be. And what we find really cool is that where people then look is they look slightly above the floor based on where they predict it's going to be after it's bounced. Now the reason we find this cool for this study is when people predict it's going to be a really bouncy ball, they tend to look really high up. When they predict it's going to be a not very bouncy ball, they tend to look really low down. So this gives us a really precise measure of what somebody is predicting at a very specific moment in time. Then once the ball catches up with where they're looking, participants then will track it quite closely at the end. So if we go back to these graphs here, what you can hopefully see is that the pink graph for autistic participants and the blue graph for non-autistic participants are actually very, very similar. We saw that overall there was very similar strategies being used and very similar sort of tracking abilities. But we did see this sort of difference here, which was happening around the time that people were making this sort of predictive eye movement. Generally, autistic people were updating their predictions much more frequently, so they were much more likely to predict these really highly bouncy balls. So whereas neurotypical participants tended to constantly sort of look lower down in sort of preparation of these normal tennis balls, autistic participants were much more likely to change their predictions. So if they got a couple of bouncy balls, they'd then look quite high up, then they'd look low down again, and they'd be much more sort of sensitive to environmental change. This ultimately meant that they were then less surprised when we gave them these really bouncy balls. So this suggests, again, that actually the ability to make predictions is not necessarily different in autistic people, but it's how predictions are being used and updated in different environments that might be different. So, taken together, what do all of these studies that I've just presented to you suggest? Well, they sort of emphasize this thing that's been researched for quite a long time, which is that autistic people generally appear to struggle a little bit more when task environments are more unpredictable or more uncertain. These differences seem to occur or be related to really sort of subtle differences in eye movements, for example, that are related to how predictions are being updated over time. Crucially, one of the sort of key findings from my PhD was this one, that actually the general ability to make and use predictions does not appear to be different in autistic people. Now, this goes against some of the high-profile theories that I talked about at the start, and it also goes back to this idea that we should be looking to change the environment. Autistic people can make and use predictions, so we need to be adapting the environment and accommodating for autistic people so they can make effective predictions and so that they can interact in an effective way. And so this comes back to this final question, I guess, that we're now really interested in researching in the next few years, is how can we make environments more predictable and more stable for autistic people to help accommodate for these differences? So Mark earlier focused on the sort of first key theme that CAAR are interested in, which is this sort of strengths-based approach. The second key thing we're interested in is the idea of developing practical applications. So we don't just do this sort of research so that we find out and can test certain theories and models. We want to do it so we can actually do things that can help autistic people in their day-to-day lives. And so we're looking to do this at the moment by looking at how we can, make sensory environments more predictable. The first sort of obvious step was just to look specifically in the context of movement skills. So you can see this is the same task that I was talking about earlier in VR. We think VR could be a potentially effective way of making environments more predictable because you can control lots of things. And you can provide sort of information like this, for example, that's giving information about what predictions could be made. It's meant to help autistic people make predictions. And we can also adapt VR so it's really sensitive to and really personalizable. So you can make it so it's unique to some of these individual predictions. We've also been doing lots of work in the last couple of years working with lots of different service providers, such as the NHS, such as education providers and training providers, specifically at how they can adapt their services to make them more predictable. So a recent example of this, I've been working with some of the NHS trusts down in Plymouth. They're working not just with autistic people, but with patients who are particularly anxious about going in for an MRI scan. For those of you that have done that before, it is pretty overwhelming. It's not a very pleasant experience necessarily. And lots of people find that very, very, very anxiety-inducing and might therefore not turn up for their scan or might move in the scanner, which can cause lots of difficulties for the NHS, obviously. And so we're trying to work with the NHS to develop new ways of making anxious people potentially less anxious. And we've been specifically working with their brilliant autism service that they have down there to look at how we can make certain things more predictable for autistic people so they're maybe less anxious when they're doing these sort of things. That's just one example there. And what we're now looking to do is to build new sort of skill programs, build new support tools that can help autistic people. You may have got the sense during this presentation that I love sport, and a lot of autistic people do love sports like tennis, but when you actually talk to people about my research, when you talk to autistic people about my research, they're maybe less interested in the specific ability to perform sports skills like tennis. They'd much rather we maybe focus on things like driving that are directly related to independence, for example. And research does suggest that skills like driving, autistic people are less likely to learn to drive, they're less likely to pass their test, and this is related to things like sensory differences, differences in relating to predictability, difference related to movement. So this is a project that we're now starting to work on, and that we're hoping that hopefully one day we'll be able to present some exciting results about in the future. And the final research theme I just wanted to touch on right at the end here is this idea that of participatory research. So this is something we're really engaging with at the moment at CAAR, and something we think is going to be really, really important. Is the idea of actually working with autistic people throughout the research process. So not just getting autistic people into the lab to do a specific test, but actually autistic people can direct what we research, the specific topics we research, how we research these topics. If we're looking at things like VR, how we build tools in VR to suit individual needs, and how we can apply our findings across the sort of real world at the end of it. And we've recently held a workshop that I think some people here might have even been to, with both autistic and non-autistic people, where we've sort of opened up to the local community to come in, and we're really trying to work with people to try and direct what we do in the research in the future, and we're really excited about doing this over the next few years. So I just want to finish by saying thank you so much for everyone that's been listening and everyone that's come along today. I did promise I'd put some resources up here, so if anyone does want to find out some more information about any of the things we've talked about, these resources are generally really, really good. And hopefully now we've got lots of time for some questions. Thank you.
So thank you very much indeed for a fascinating talk where research, not just exploring a topic of enormous importance, but actually changing the way people think about it as well, which I think is an amazing achievement.